All right, we're going to do our last day of probability. We're going to talk about some different probability distributions. So, to get us started, a gaming software company with 5 games on the market is interested in how many games each of their customers play, so they surveyed 800 randomly chosen customers. We're going to assume that they chose those customers in a way that makes it a fair sample and that there's no bias involved. We're just going to assume that that all happened correctly. So we've got 800 customers surveyed here. And the way to read this table is that 130 of those customers play one of this company's games. 300 of these customers play 4 of the games. 110 play 5 of the games. So number 1 says find the probability that a randomly chosen customer plays 3 games. Well, how many customers play 3 games? So if we're thinking about just probability, right? So the key is the number of successes over the total number of possibilities. Well, there's 800 customers to choose from. How many of them would make us happy, meaning that they play 3 games? 150. We're going to assume that this means plays exactly 3 games, right? So that's 15 over 80. Divide that by 5, and we get 3/16, which is 18.75%. So out of these 800 customers, if you chose one, you had an 18.75% chance that you would have chosen somebody that plays 3 games. Okay, let's kick it up a little bit here. Find the probability that a randomly chosen player plays at least 4 games, right? So again, there are 800 players that we could choose from. We're assuming this is a new draw, and we're not worried about who we drew first, and we're not doing 2 different choosings here. So there are 800 customers to choose from. How many of them play at least 4 games? Well, these folks play 4 games, right? But these ones play 5. Is 5 at least 4? Yeah. So we need to look at all of those. So that's going to be a total of 410, right? The 300 that play 4 and the 110 that play 5. So that would be 41 over 80. 41 over 80 is 51.25%. So just barely over half play at least 4 games. Instead of a frequency table, which, let's go back, is what this is called, right? This is a frequency table. It shows the frequency with which certain outcomes happen. So one computer game being played occurs at a frequency of 130 customers. Okay, so this is a frequency table showing how many times something occurs. A probability distribution is a very similar chart, but instead of showing the frequency at which something occurred, it shows the probability of each possibility occurring, which is probably a lot more useful, right? Because if I'm using a frequency chart or frequency table, I'm going to need to know how many people I'm looking at, and that's only going to be how many times something occurred in that sample. And I probably want to know something more about the entire population, so I'm going to be turning those into probabilities anyway. So we've got a probability distribution, which would be like the same left side, 1 game, 2 games, 3 games, 4 games, or 5 games, but instead of showing the number of things, number of players, it would show the probability. So this one would be 0.1875 instead. That's the only one we did, but we would find these probabilities instead of the frequency. Hope that makes sense. A probability graph is exactly the same as a probability distribution, but instead of it being a chart, it's a bar graph. We just turn that chart into a graph, is all it is. There are a couple of things that need to happen with regard to probability distributions, and that is that the probability of each outcome, which is what X stands for, is greater than or equal to 0, right? You can't have a negative probability, and is less than or equal to 1. Something can't be more than 100% likely. Either it never happens, or it always happens, or somewhere in between. But 110% doesn't make any sense. The other really important thing is that the sum of the probabilities is 1, right? If you add up all of the probabilities for all of the options, you need to get 100%, meaning there are no other outcomes not accounted for in the probability distribution. Okay, so let's take a look at one. So this is the probability distribution for the blood types of the general population. So 41% of the general population has type A, 12% type B, 3% AB, and 44% O. So when it says to show that the distribution is valid, what that means is show that the probabilities when added together, are going to give us 100% or a 1, right? Because otherwise that would mean that there's some population that's not accounted for in this table. I would want to know, well, what is the blood type of the other 3% or whatever the difference is? So if you add up 41, 12, 3, and 44, you will get 100%, which is exactly what we want. Okay, so let's look at the questions. What is the probability of each of the following? Probability of type A or type B. Now, are they mutually exclusive? Can you be type A and type B? If you've taken much biology, you know the answer is no. Type AB is not A and B. It's a different type completely. So that means that we're just going to take the two probabilities and add them. So the probability of type A or B would be 0.53 or 53%. Okay. Probability of not O. So if it's not O, that means it's anything else, right? It's just not O. So there's two ways to do this. We can either add up 41 plus 12 plus 3, or if it's not 44%, it has to be the rest of it, because, right, it all has to add up to 1, so we can use that to our advantage. And we're going to get 56%. So you have a 56% chance of not having type O blood. You have a 53% chance of being type A or type B. Number 3, make the probability graph. So here's what I'm going to do to make this a little bit easier. I'm going to copy this guy. Oh, no, I'm not. I'm going to jot the table down over here so we can see a little bit better. So let me get my pen back out. So we've got type A, B, AB, and O. A was 41%, B was 12%, O was 44%, and AB I think was 3%. Let's make sure those are right. 41, 12, 3, and 44. Good. So we need to make 4 bars. So we need to have an A, a B, AB, and O. We need to choose a scale. I only have 4 or maybe 5 tick marks to work with. The highest that we go is 44. So let's make this 10% each. So 10%, 20%, that's terrible percent, 30%, and 40%. A is 41%, so just barely above 40, somewhere up there, right? Whoops. B, 12%, so a little bit above 10. AB is 3%, so maybe a third of the way up to 10. And O is 44, the highest one yet. So we're coming all the way up, almost halfway to 50 from 40 and back down. Not the prettiest graph, but you get the idea, right? And then the tops of each of these would need to add up to 100%. But this is what a probability graph would look like. It's just a bar chart version of this table. It's all it is. It's frozen. Here we go. The Professional Golf Association, the PGA, is interested in the age of golfers in order to recruit more players. The probability distribution is shown below. So, 1, show that the distribution is valid. So let's look at this table. We've got ages grouped, so 18 to 24, 25 to 34, 35 to 44, 45 to 54, 55 to 64, and 65 plus. So to show the distribution is valid, we just need to add up 0.13 plus 0.18 plus 0.21 plus 0.19 plus 0.12 plus 0.17. Take a second and verify that that actually does equal 1, and if not, we need to look at why that might be the case. Lucky for us, this turns out to be 1, so that's 100%. If you look at this table for a second, you might have a question about how 100% of the golfers could possibly be included in this. So we've got everyone 65 and older. Okay, so that goes all the way up to the oldest person. That makes sense. Then we've got 64 to 55, 54 to 45. So nobody can be between 54 and 55. You're either 54 or 55, and that works all the way down to here. But what about lower than 18? I would imagine that some of you are golfers who are under the age of 18, right? So we're just going to assume that to join the PGA, you have to be 18, and so they're only looking at their membership. But obviously, there are golfers under the age of 18 that this table would not be representing. So we're just going to assume that it's members of the PGA and that you have to be 18 in order to join. Number 2, calculate the probability that a golfer is 45 or older. Define your x variable first. So we need to decide what x is going to be equal to. There's a little bit of hint down below, but x should probably be the age of a golfer. Okay, so that we can find the probability that x, or a golfer, is greater than or equal to 45. Okay, so we need to figure out what our chances are here. We can't do a probability because I don't know how many people we chose from. So what we're going to have to use is just the probabilities themselves, which is fine. So let's start with 45. What's the probability that somebody's 45? Well, 45 to 54 is 0.19. Or you could be in the next group, right? So we want this group or this group, 12%, or this group, 0.17. So those three groups include everybody who is 45 and older. We add all three of those up. 19 and 12 is 31, plus 17 is 48. So 0.48 or 48%. So this would show that almost half of the golfers are 45 or older. You can see why the PGA might be worried about recruiting younger members and more players if half their membership is 45 or older. It's not great for the longevity of the membership. Wrong way. Okay, so let's go back to that first example, the video game company. Let's calculate the average number of games played by each customer, or by any customer, right? So we want the average. So average means we're going to have to do the total number of games over the number of players. So the bottom is easy. Bottom is going to be 800 players. So next we need to figure out how to calculate the number of games played. Well, 130 customers play one game. 110 customers play two games. So if we're counting the number of games played, that's actually 2 times 110, right? The 110 people times 2 games each. Then we've got 3 games times 150 players, because 150 players play 3 games each, plus the 4 games times 300 players, plus 5 games times 110 players. So if we add all of that up, 130 plus 2 times 110, plus 3 times 150, plus 4 times 300, plus 5 times 110, we're going to end up with, let's give myself some room, 2,550 games played by 800 players, which means we're going to get an average of 3.1875 games per player. Now, obviously, you can't play 0.19 games, but that's just an average, right? So that's the long way of doing this. There is a little bit better way. If we use, why is that button not work? If we use the efficient way. So first, let's make a probability distribution. So I want to find the probabilities of playing 1 game, 2 games, 3 games, 4 games, or 5 games. So let's say that's the number of games, x, and this is the probability of x. So 1 game is 130 out of 800, right? We're assuming this is a fair sample. So we can assume that this would work for the entire population. So that's going to be 0.1625. 0.1625. Probability of playing 2 games would be the 110 players who play 2 games times 2, right? Nope. We don't need to do that, do we? We're just looking at players. So 110 over 800. 1375. And we're going to keep doing that for each of these rows. So then I take the 150 divided by 800. I'm just finding what's the probability that a player is in each of these groups. That's all we're trying to do. 0.1875, that's the one we did before. 300 divided by 800, that's going to be 3/8 or 0.375. So 375. And then 110 divided by 8 would be the same as in 2 games, so 0.1375. So this is the probability distribution. This shows the probability that a person is in each one of these groups, right? So if instead of finding the number of games divided by the number of players, if we just found the number of games played by each probability, and we did 1 game times 0.1625 plus 2 games times 0.1375 plus 3 games times 0.1875 plus 4 games times 0.375 plus 5 games times 0.1375. Go ahead and pause the video and calculate this real quick, and let's see what you come up with. Okay, so we're adding up 1.1 times 0.1625 plus 2 times 0.1375 plus 3 times 0.1875 plus 4 times 0.375 plus 5 times 0.1375 again. And what are we going to end up with but exactly 3.1875, which is what we came up with last time, but without having to add up all of the games played by each player. Now, this wasn't so bad for 5 tables, but if we had more, this would be a lot harder, right? So that's what's called expected value. Okay. The expected value of a discrete random variable, discrete meaning like 1, 2, 3, 4, 5, it can't be partial values, you can't play a partial game, is the weighted average of the values of that variable. It's calculated by finding the sum of the products of every possible value and its associated probability. So that's a really difficult way to describe what we just did. Let's look at this down here real quick. This is the general formula up here, but I've got a specific example that I think will make more sense. So, an example, a fair 6-sided die. So this is just a regular die, right, that you might play Monopoly with. There are 6 outcomes. 1, 2, 3, 4, 5, and 6. Each outcome has an equal probability in this case. You have a 1 in 6 chance of rolling a 1, a 1 in 6 chance of rolling a 2, a 1 in 6 chance of rolling a 4, and a 1 in 6 chance of rolling a 6. The expected value of a die roll is the outcome multiplied by its probability plus the next outcome multiplied by its probability plus the next outcome multiplied by its probability plus, and you just keep doing that. So 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6, etc., etc. So you can see that that would be 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. 1 plus 2 is 3 plus 3 is 6 plus 4 is 10, 15, 21/6, or 3.75. Sorry, 3.5. The expected value of a die roll is 3.5. So, for example, if I offered you a game where I give you a die and you roll it and I pay you as many dollars as come up, if you play that game 100,000 times, you could expect to win $3.5 on average per roll. That does not mean you're going to get $3.5 on every roll. Some rolls you'll get 6, some rolls you'll get 2. But on average, if we played that game a lot of times, 100,000 times, a million times, or whatever, your expected value, the amount you can expect to win over time, is $3.5 per roll. Okay, it's a great way to figure out what the chances of something happening long term are. So, expected value with 1 in probability. So these are called odds when you see a 1 in 15 or 1 in 50. So an insurance company has collected the following data on the probability of an alcohol accident causing a certain amount, and the company is wondering what to charge for their 6-month policy. So they're saying that 1 in 15 drivers will cost them $1,000 in a 6-month period. 1 in 50 drivers will cost them $5,000. 1 in 150 will cost them $10,000, and 1 in 400 cost them $20,000. So the first thing we have to do is turn these into probabilities. So we're just going to divide 1 divided by 15. We're going to get 0.067. 0.067. 1 in 50 is 0.02. 1 in 150 is 0.0067, so not very likely, and 1 in 400 is 0.0025. Okay, so I'm just dividing 1 by 400, 1 by 150, 1 by 50, and 1 by 15 to get those, right? So we need to make sure this is a valid probability distribution. So if we add all these up, 0.067 plus 0.02 plus 0.0067 plus 0.0025, if we add all those up, I get 0.0962 or 9.62%. That doesn't make any sense. Didn't we just say this has to add up to 1? Well, there's a category here that we're not counting. How about $0, right? Everybody else is going to cost them nothing. Most drivers don't get in an accident every 6 months. Now, most drivers do get in an accident. That is true. But that's over their lifetime, not in a 6-month period. They're only looking at 6 months, figuring out how much are we going to pay out every 6 months, so how much do we need to charge everyone? Because that's how insurance works. They figure let everybody pay a little bit all the time, and then we'll use that giant pot of money to pay the people who have accidents when they have them. Most of you will pay insurance for your car for a long time before you ever need it, which is a good thing because you won't be in accidents. But what's really happening is you're paying for other people's accidents until you have one, and then everybody else chips in to help you pay for yours. So the rest of the 81.38% would be 1 minus the 9.62, cost the company nothing. So when we go to figure out what this expected value is, meaning what is the expected payout for an individual person, we're going to take the 0.067 times $1,000, and we're going to add 0.02 times $5,000 plus 0.0067 times $10,000 and the 0.0025 times $20,000. Then we're going to do the 0.8138, this 81% that cost them nothing. Now what happens when I multiply 81% times nothing? That whole thing becomes 0, right? So really all we're doing are the ones that actually cost money. But that's why this is still a valid probability distribution, even though the values we're working with don't add up to 1. So let's do 0.067 times 1,000 plus 0.02 times 5,000 plus 0.0067 times 10,000 and then 0.0025 times 20,000. That means that the expected driver, or at any average driver, is going to cost this company $284. So if they take all of the accidents they expect to have to pay for and divide by all of their members, any individual is going to cost them $284. And that works no matter how many drivers there are, because every time they add a driver, they get more money, but their risk of having to pay a driver goes up just a little bit, right? And this is where what's called actuarial sciences comes in. It's a math field that specializes in figuring out how risky a specific driver is. Because you'll notice not everybody pays the same amount in car insurance, not even close. Right? So it's not just saying, oh, well, every person's going to cost us $284, so we'll charge everybody $350. That way the company makes money too. That's their goal, right? That's not what they're going to do. They're going to say, well, hey, this 17-year-old boy is going to be a lot riskier driver, so we're going to charge him more than we're going to charge this 58-year-old woman who's a lot more mature and calm and less likely to be driving aggressively. There are a lot of different factors that go into actuarial sciences. Everything from your age, your grades. You actually get a discount on your car insurance if you have good grades. So if you're not driving already, when you are, your parents are going to be wanting you to keep your grades up. To the type of car that you drive. You're more likely to drive aggressively if you have a sports car, a Mustang or a Corvette, than you are if you drive a Ford Bronco or a Honda Civic. Just because the kind of person that's attracted to the sports car is also more attracted to driving fast. So there's a lot of things that go into that. And if this is interesting to you at all, actuaries, the people who work for insurance companies, figuring this stuff out, it's an actual license you have to get, just like being a CPA or a lawyer. There's a license you have to earn, but actuaries easily make 6 figures You need a degree in mathematics, and then you need to take the actuarial exams. I'd be happy to talk to any of you any more about that if you're interested. I think it's a really interesting field. It's a lot of crunching numbers and looking at statistics. But if that's something that's interesting to you, there's a lot of good money in it. But anyway, that's a specific and very common use for our expected value. Um, it's a way to kind of predict what any one person might do given statistics about a large group. But that's it for expected value. You're on to the homework. Have a great day.